Let's begin with a brief review of what we did last time, and then we'll move on to discussing two new topics, curvature and the so-called F4W universe. The F4W universe is essentially the geometry we use to model an expanding universe. And this expansion is set by whatever stuff there is in the universe. So for example, the universe will expand differently if the dominant contribution to the energy density is radiation, or will expand compared to the dominant contribution is matter, or as it is today, the cosmological constant, the so-called vacuum energy density, which is embedded in space-time itself. Okay, so before we start the review, are there any questions from last time? You have a question? Okay, so so one of the ideas that Einstein presented in special relativity was the notion that you shouldn't think about space and time as being different. So in the original Newtonian conception of classical mechanics, the idea was that time is infinite, and space is also infinite, and the idea was that different observers agreed on coordinates of events in space-time. So every observer, according to Newton, would give coordinates t, x, y, z to an event which occurred. What Einstein did in special relativity was he refuted the notion of simultaneity. So things which are simultaneous from a Newtonian perspective, because all observers agree on the coordinates t, x, y, and z, is no longer true in special relativity, because different observers will disagree on these coordinates. One of the classic experiments that the Duncan experiments demonstrates this is the idea of lightning striking a train. So if you have some train that's moving along, and a bolt of lightning hits the front of the train, the observer at the front of the train and the observer at the back of the train will have different measurements of when the lightning struck the train. This is a consequence of the motion of the train. The observer standing here, for example, on the outside of the train will have a different measurement as the observer standing here. Okay? So the idea of simultaneity was lost in special relativity. Now, the thing which replaced Newtonian mechanics was a conception of space and time as being related to each other. So you can imagine because these observers have different coordinates, t, x, y, and z for this event, physics is physics. So this observer has to go and calculate what this observer sees. And similarly, this observer has to calculate what this observer sees. And the way these calculations are given is by something called Lorentz transformations. Lorentz transformations relate space and time to each other. And it's in this sense that space and time are on equal footing. We'll see what this means in general relativity as we proceed today. We'll see that measurements, for example, lead to an invariant distance that all observers will agree on. This invariant distance invokes both time and space. Other questions? Okay, so last time we discussed the so-called equivalence principle. The equivalence principle is at the heart of general relativity, and it basically says the inertial mass equals the gravitational mass, although Newtonian mechanics in principle is different concepts. So again, Einstein had a thought experiment. This thought experiment involved the so-called Einstein elevator, and in the elevator, someone is falling due to the force of gravity. This gravitational acceleration the person experiences leads to a force which is minus v Newton, mass of the Earth, of the Earth over r squared in the radial direction. So the alternative is to think of a person in an elevator still. The elevator is on a rocket ship accelerating at a. Here the force the person experiences is the inertial mass times its acceleration a. So Einstein tells us that this inertial mass is the same as its gravitational mass. Okay? So based on this observation, we then examined what happens to light in the elevator. So the elevator, because of its motion, when it's on a rocket ship, the light will bend downward if it's launched straight over here. So consequently, because observers will agree on the behavior of light, since the gravitational field is indistinguishable from the acceleration, in the gravitational field, the light will also bend. So Einstein was aware of Fermat's principle. Fermat's principle asserts that light takes the least time to travel between 2 points. Special relativity also told us that the speed of light is a constant that all observers agree upon. So, combining this observation with Fermat's principle says that light travels the shortest path between 2 points. The shortest path between 2 points is called a geodesic. So light travels on geodesics. Now, here we see from the picture that light is not traveling on a straight line. Okay? So light is not traveling on a straight line. Therefore, a straight line is not a geodesic. We know that in flat space, the shortest distance between 2 points is a straight line. Therefore, the conclusion is we aren't in flat space. Okay? Yeah?
Is Fermat's principle, has it been proven?
It's something you can derive, yes. So the conclusion then is that we aren't living in flat space, we're living in a curved geometry. So today, we'll explore what curvature in geometry means. Okay. So now, we have a change in worldview from what Newton taught us about gravity. So Newton worked in a theory of universal gravitation. So universal gravitation says that mass tells gravity, instantaneously, how it accelerates. So how is it? Mass tells gravity how to exert a force. And accelerate. And this acceleration is basically a property of this quantity called mass that we associate with the object. So it's independent of the composition of the object, it's independent of the structure of the object, or the color of the object, or whatever other feature. There's only just one quantity mass we associate with this object. It determines how it moves in a gravitational field, according to Newton. According to Einstein, objects have energy and momentum. This energy is related to the rest mass of the object, equals mc squared. And the presence of energy and momentum curves space-time. And this curvature means that objects move as a response to the geometry. Okay. Now there's a famous equation that describes this. So the equation here is F equals minus g Newton mg over r squared r hat. And the equation here is r mu nu minus 1/2 g mu nu r equals 8 pi d Newton over 2 to the 4th t mu nu, where t mu nu represents the energy and momentum, and the left-hand side of the equation tells us about curvature. Okay? So Einstein also resolves the action at a distance issue in Newtonian mechanics, where objects respond instantaneously to the presence of other masses. Okay? So that's what we discussed last time. This time I want to be a bit less qualitative and a bit more quantitative and precise about what we mean by curved geometry. Okay, so we'll begin with Euclid. So one of the things that Euclid showed was that on a plane, if you draw a triangle with internal angles alpha, beta, and gamma, what do you know about these internal angles? Yeah. Yes. So alpha plus beta plus gamma. Okay, so suppose we draw a triangle on a sphere. What do you suppose the angles sum up to? Right, so the point is that the angles are bigger than 180 degrees. So you can imagine a right triangle where this arc intersects the equator. So you have one point here. This arc, this line of longitude, intersects the equator at a right angle. Any line of longitude intersects the equator at a right angle. So there are two right angles already. And this angle is arbitrary. So as a result, for a general triangle, you can show that alpha plus beta plus gamma is bigger than pi radians. Okay. So we already are aware that if we have curved geometry, so it's intuitively clear to us that the Earth is curved. On a curved geometry, the sum of the angles need to add up to 180 degrees. So the sphere is an example of a geometry with positive curvature. So what would a geometry with negative curvature look like?
Okay, inside of the sphere.
No.
Yes. Would it be like something like a second?
Yes, it's exactly the same. So it's got some geometry. Just vaguely like that. So on a saddle, you can imagine a triangle with angles that sum up to 0 degrees actually. So here, alpha plus beta plus gamma is less than pi. So this is a geometry with negative curvature. Okay. So we can in fact show that alpha plus beta plus gamma equals pi plus a parameter kappa times the area of the triangle divided by r squared, where r measures the radius of curvature. So r here, for example, is the radius of the sphere. R is some parameter associated to how bent the saddle is, in the negative curve example. And kappa is equal to 0 in flat space, so that alpha plus beta plus gamma equals pi. Kappa is equal to 1 for a positively curved geometry, and kappa equals -1 for a negatively curved geometry. Okay, so let's review Pythagoras. So this is probably a familiar calculation, but I want to remind you that we can change coordinate systems. And we'll do a more complicated change of coordinates later on in the lecture. So, suppose we've got coordinates x, y, and this is x plus delta x, y plus delta y, and this forms a triangle. So the distance between here and here is given to us by the Pythagorean theorem. So I'll call that distance ds squared is delta x squared plus delta y squared. And if we have differential distance, if we're taking, for example, limits between points, we can write this as dx squared plus dy squared. Okay? So that gives us a measurement of the distance between these 2 points on flat space. Now, if we're working in polar coordinates, x is equal to r cosine theta, and y is equal to r sine theta. So dx equals 1. we differentiate this expression. So dx equals dr cosine theta minus r sine theta d theta. Similarly, dy equals what?
Sin theta plus cos.
Exactly. So let's square these things. Dx squared is dr squared cosine squared theta plus r squared sine squared theta d theta squared minus 2r dr d theta cosine theta d sine theta. And dy squared is dr squared sine squared theta plus r squared cosine squared theta d theta squared plus 2r dr d theta sine theta cosine theta. Okay? So when you add these together, what do you find? You find that this term cancels that term, and you find that cosine squared theta plus sine squared theta is 1. So this equals dr squared plus r squared d theta squared. Okay? So if you had measurements here, you had coordinates here, r theta and r plus dr theta plus d theta as your coordinates for these 2 points. You can measure distance between these 2 points not just as dx squared plus dy squared, but as dr squared plus r squared d theta squared. Okay? And the measurement you find for that distance should be independent of what coordinate system you choose. Yeah.
Sorry if this is a very stupid question, but for when deriving dx, should we not write that as a row vector? Because you're first deriving with respect to r and then deriving with respect to theta.
So I'm just using product rule here. So dx is dx dr plus dx d theta d theta.
Oh, yes.
Okay, so let's measure distances on the sphere. So this is equator. And let's consider, so without loss of generality, we can choose one point near the North Pole. Just call the point you're standing on the North Pole. Okay, so that's one point here. And we're measuring the distance to some other point there. This radius is the radius of the Earth, so that's r. And we have 2 coordinates here. So this is a circle of latitude, and we have some angle theta describes what this latitude is. Okay, that's one coordinate. So to measure where a point is, we have to specify 2 coordinates on the sphere, latitude and longitude, if you like. The other angle is the angle on the circle, which goes from 0 to 2 pi. Okay, so this angle here on the circle from the center of the circle, so let's say this is 0, this angle here is pi. Okay, so the point is specified by coordinates theta, and phi. So theta is between 0 and pi. The 0 is the North Pole, and pi is the South Pole. And phi is between 0 and 2 pi. This is the angle on a circle. Does anyone understand this picture? Should I go over it again? Okay, so in order to specify the location of a point on the sphere is two-dimensional. The surface of the sphere is two-dimensional. Because the surface of the sphere is two-dimensional, it's giving me two coordinates. These coordinates are typically latitude and longitude. Okay? So I want to define the latitude as the angle away from the North Pole. So at the North Pole, this angle is 0. But if I'm down here somewhere, I need to tilt. And the tilt is given by this angle theta. At the equator, theta is equal to pi over 2. The South Pole, theta is equal to pi. Okay? So theta runs between 0 and pi. If it's bigger than pi, it's the same as, so suppose we had, so I claim this angle here is pi. So suppose we wanted to make an angle bigger than pi. It would be the same as, so suppose we wanted to have this here. It's the same circle latitude as over here. So the angle is smaller than pi. Okay? So this angle theta runs between 0 and pi. So that just puts me on this circle somewhere. The circle of latitude. So you specify an angle on that circle of latitude to tell you where this coordinate is. That angle can be anything between 0 and 2 pi, or 360 degrees. So the second angle is between 0 and 2 pi. Yeah?
So when you said that the surface of the sphere is 2D, but surely if the surface of the sphere is curved, we can only tell if it's curved in a 3D coordinate system?
It's embedded in 3 dimensions, yes. But it's the surface itself is two-dimensional. Any point can be specified by 2 coordinates, so it's two-dimensional. Okay, so what is this distance from the North Pole? We'll call this distance little r. So little r is equal to r times the angle. Exactly. So if theta was equal to pi, then r would be 1/2 of the circumference of the circle. The circumference of the circle is 2 pi r. So theta is equal to pi r means that r is equal to pi r, or 1/2 the circumference. Okay? Because the circle is homogeneous, whatever this angle is basically tells you what the distance is from the North Pole. Okay? And this distance to the North Pole is independent of the angle phi. Because wherever you were on the circle of latitude, you'd measure the same distance to the North Pole. So the maximum distance between 2 points on the sphere is pi times the radius of the sphere. Okay, the North Pole is as far from the South Pole as you can get. And we know that distance is pi times the radius of the sphere. Now, let's measure distances here. So, North Pole has coordinates 0, 0. South Pole's got coordinates 0, 0, pi, 0. The distance is going to be given by, so let's work in 3 dimensions. We know the sphere is embedded in 3 dimensions. The sphere is a surface, x squared plus y squared plus z squared equals capital R squared. Okay, so that's what defines the sphere. So there are 3 coordinates with 1 constraint between the 3 coordinates. Therefore, 3 coordinates minus 1 constraint tells us this is a 2-dimensional geometry. Okay. So, df squared is given by dx squared plus dy squared plus dz squared. Just like on Euclidean plane, ds squared was dx squared plus dy squared. Okay, so what are x, y, and z? X is equal to r sine theta sine phi. Y is equal to r sine theta cosine phi. I don't want to write this. Where is this? I guess I want cosine here, sine here, and z is equal to r cosine theta. Okay. So, if we repeat this exercise, which I'll leave for you to do in the tutorial, you'll find that df squared in these coordinates theta and phi is equal to, stay, r squared d theta squared plus sine squared theta d phi squared. Okay? Here, there are 3 coordinates, but there are only 2 parameters here, d theta and d phi, because the radius is fixed. If the radius was not fixed, if, for example, we're looking at a 3-dimensional distance between 2 points in 3-dimensional space, then we would find that ds squared was going to be equal to dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. But because the radius is fixed, dr is equal to 0, and r is equal to capital R, we get this formula here. Okay. So these coordinates are called spherical polar coordinates. And they're convenient for measuring distances on the sphere. Here, remember that theta is the ratio between the distance along the sphere and the radius of the sphere. So you can always plug in theta into this formula here. Okay, see what happens when you do that. So theta is equal to r over r, d theta is equal to 1.
Sorry, you said capital R was fixed, right?
Capital R is fixed.
So it's just 1 over R.
Yeah. Yeah.
Is it not dr over?
Is dr over r. So df squared is r squared, d theta squared, or dr squared over r squared, plus sine squared r over r d theta d phi squared. Or dr squared plus r squared sine squared r over r d phi squared. Okay. So the sphere was positively curved. and we associated this with kappa equals +1. The saddle was negatively curved, and this is kappa equals -1. So what do you think the distance is on the saddle? ds squared equals what? It turns out that the distance is just dr squared. So r is, so in the saddle, it's the distance from the center of the saddle, just like we have looked at distances from the North Pole. Dr squared plus r squared is the curvature of the saddle, and the sine becomes a sinh. Okay, so unlike the sphere, the distance between 2 points has no maximum. Likewise, unlike the sphere, the area of the negatively curved space is infinite. Okay. Okay. So far, we've looked at 3 different kinds of geometries: flat geometries and positively curved, negatively curved geometries. The ds squared is called the metric line element. What's wrong with this word? It measures the distance between 2 points. Now, we can write ds squared as dr squared plus s kappa of r squared d omega 2 squared. So d omega 2 squared is the line element on a sphere. So this is equal to d theta squared plus sine squared theta d phi squared, and s kappa of r equals r sine r over r, for kappa equals +1, r for kappa equals 0, and r sinh r over r for kappa equals -1. Okay. So what the metric line element is, it's a ruler in a curved space. So it measures distances based on the curvature of the space. If it's positively curved, you measure one distance. It's negatively curved, you'll measure another distance. It's flat, you measure yet a third distance. Okay? So if you plug in, for example, s kappa squared equals r squared, the flat space case, it will cover the metric that I erased for three-dimensional flat space. So the first term for a sphere, for example, in flat space, basically measures what the radius of the sphere is. Once you measure this distance r, then you measure the distance between 2 points that are separated by different angles. Okay? So in the flat space example, ds squared is dr squared plus r squared d theta squared plus sine squared theta d phi squared. This first term measures which sphere you're on. Once you figure out which sphere you're on, then you measure which circle of latitude you're on. Then you measure which angle you're at along that circle of latitude. Okay? And the circle of latitude is weighted by the radius of the sphere, and the distance on that circle of latitude is weighted by the angle. Okay, so this is the flat space. Similarly, if you're in a curved space, you also have an additional weighting factor corresponding to the radius of curvature of the geometry you're on. Okay. Okay, so let's look at the limit as r goes to infinity. Capital R goes to infinity. So if capital R goes to infinity, the denominator here becomes very, very small. So the Taylor series says that only the leading term should matter, since this is a very small parameter. So the leading term in the Taylor series for sine and sinh is linear term. So leading term sine x is x plus dot dot dot. Sinh x is x plus dot dot dot. So let's just look at x, and we have r squared. So we have s kappa squared. And the limit where r goes to infinity is r times r over r squared, which is r squared. Similarly, this is for both kappa equals plus 1 and kappa equals minus 1, since sine x is approximately x, and sinh x is approximately x. Okay? So in the limit where r goes to infinity, s kappa is equal to r squared, which is the same as a flat space answer. So you have a sphere with an infinite radius that's the same as being in flat space. Okay, so one thing we've noticed is that the metric line element is not unique. You can measure distances in whatever coordinates are convenient. So the ruler you pick isn't unique, it just needs to give you the same measurement as someone else's ruler. So for example, in flat space, I can work with a ruler with x, y, and z as my coordinates, or I can work with a ruler as r, theta, and phi as my coordinates. I should get the same answer. I should get the same answer, and I will get the same answer because I know how to convert x, y, and z to r, theta, and phi. I wrote down the coordinates change that enables us to go from one set of coordinates to another. So ds squared is dx squared plus dy squared plus dz squared, and this is the same as dr squared plus r squared d theta squared plus sine squared theta d phi squared. Okay, so either x, y, z, r, theta, phi, or whatever else you pick, gives you the same distance, but the metric line elements are different in different coordinate systems. Okay, so one thing I can do is I can define a new variable, c, as s kappa of r. If I define this new variable c, my metric is ds squared equals d c squared over 1 minus kappa c squared over r squared plus c squared d omega 2 squared with this change of variables. So I can measure with this metric, or I can measure with that metric, I'll get the same answer. In that case, previously I was using r, theta, and phi. Now I'm using c, theta, and phi. Same thing. It's just a change of variables. So this is one of the principles of general relativity. It goes under the name general covariance. And this is where general in general relativity comes from. So these are the two basic ideas that inform general relativity. One is the equivalence principle, which you've already seen. The other is the notion of general covariance. What general covariance says is that coordinates are labels. They have no intrinsic meaning. You get the same physics in a different coordinate system. And as a statement of, it also goes under the name diffeomorphism invariance. Same physics under a change of coordinates. If you measure the distance between 2 points, any coordinate system, we get a number. How many meters are we from somewhere else? Light travels along that shortest distance between 2 points. Light travels at a constant speed. So the physics of light going from here to there, that's coordinate independent. That has a physical meaning. The coordinates you assign to the 2 points light's traveling between, that doesn't have an intrinsic meaning. One is physical, one is not physical. Okay, so light light travels the shortest distance, and this travel time, or this distance equivalently, is a physical thing. And therefore is coordinate independent. Any questions? Okay, we're halfway through. Why don't we take a short break? Yeah.
Sorry, when you say over here, x squared plus y squared plus z equation gives us that's 3 equals 3 constraints for the sphere.
So equals r squared firstly. Secondly, we have 3 coordinates, x, y, and z. So you imagine the coordinate system at the origin of the sphere, the center of the sphere, and you can measure how far your point is using 3 coordinates x, y, and z. One of those coordinates is redundant. It's redundant because the 3 coordinates x, y, and z you get need to satisfy this equation.
Because if you have 2, then you can automatically
Yeah. Yeah. Okay, so the distance is the same as with the sphere. So for the saddle, it's just sort of curved. It's curved oppositely, but just like a sphere, there's this radius r, and there's a distance from the North Pole, little r. In the saddle, there's the curvature of the saddle is given by some parameter, and distance r is distance in the center of the saddle. The curvature is given by some parameter here, capital R. Okay? Just like this curvature of the sphere is given by the radius of the sphere. So if you like the radius of the saddle. And r is the distance along the saddle. Just like little right here is the distance along the sphere. Okay, should we continue? So far, everything I've said is about spatial distances. I haven't really talked about how time fits into this. And as we said, space and time should appear on equal footing in special relativity and general relativity. How does time fit into the story? What we do is, because we've got an extra coordinate, so instead of t, x, instead of just x, y, and z, we have t, x, y, and z. Or instead of just t, r, theta, and phi, instead of just r, theta, and phi, we've got t, r, theta, and phi in these universes. We can figure out how metric distances involve time. So the answer is that df squared in flat space is minus c dt squared plus dx squared plus dy squared plus dz squared. Okay, so this is called Minkowski space. And it says that, okay, so we need c here in order to multiply time. When c multiplies time, we get a distance. C is meters per second, time is second, multiply that to get a meter. So c dt is a distance, and because you're adding into distances squared, it needs to be squared as well. So that's why there's a c squared dt squared. That's not very mysterious. The mysterious bit is the sign. There's a minus sign in front of the time term and a plus sign in front of the space terms. So the sign basically tells us that if you measure distances in space-time traveled by light, that distance is 0. Okay, so this sign tells us that light travels a distance ds equals 0 whenever it goes for any 2 points in space-time. You assign to the points in space-time can be anything at all. The light that travels between these 2 points, however, always travels ds equals 0. That sign ensures this happens. Yeah.
So sorry, how did you derive that statement just from the sun?
Well, I'm just telling you this is what happens. So I'm not deriving it for you. I'm just saying, if you like, this is a definition.
Okay.
So we're constructing the geometry such that there are certain geodesics which connect 2 points in space-time. Light travels along those geodesics in space-time and measures the distance 0. So 2 events they're connected by a ray of light are so-called null separated. Null means the distance between the 2 points is 0. Okay, so let's see what this implies. Let's work in polar coordinates. It's a bit easier. This is minus c squared dt squared plus dr squared plus r squared d omega 2 squared. Okay, so that's just a change in variables from x, y, and z to r, theta, and phi. Okay, so suppose light was traveling between 2 points, r Let's say T1, R1, theta 1, phi 1, and T2, R2, theta 2, and phi 2. What do you know about theta 1 and theta 2 and phi 1 and phi 2? Yeah,
They're not the same.
they're the same. So, because it's light traveling, and space-time is smooth and homogeneous, there's no reason for light to change its angle. Okay? It's empty space. Light's just traveling in some particular direction. It keeps traveling that direction. Therefore, the angle can't change between 2 points that are connected by a ray of light. Okay, so this tells us that d theta equals 0 and d phi equals 0. Okay? So d omega 2 squared was d theta squared plus sine squared theta d phi squared. So this equals 0. This tells us then that ds squared in these coordinates is minus c squared dt squared plus dr squared. Okay. I just told you that light travels 0 distance along a light ray. So this equals 0. So let me rearrange terms. I have minus c plus c squared dt squared equals dr squared, or dr dt equals plus or minus c. So as you measure the change in the distance with respect to time, that's equal to the speed of light, because it's light traveling along the light ray. That's probably too low. Okay, so what do we, okay, so this is just flat space so far, the story of flat space. What do we know about cosmology on large scales? What do we know about what the universe goes like? Yeah.
It's homogeneous and isotropic.
Okay, so it's homogeneous and isotropic. Homogeneous means the same at each place. Isotropic means the same in each direction. So because it's the same in each direction, the physics needs to be invariant under changes in my coordinates in theta and phi. So I can choose my angle theta equals 0, my angle phi equals 0, any direction I like. And the physics needs to be the same. This means there's a spherical symmetry in my space-time. Any angle on a sphere is exactly the same as any other angle on a sphere. I can orient my coordinate system such that that's the North Pole. Okay, so what does homogeneous mean in this context? So we know that the angles are the same, so there's a spherical symmetry embedded in our metric, whatever that metric happens to be. What about distances? Yeah.
They're also the same.
They're also the same, up to one minor tweak. What's the tweak? We introduced a new coordinate, right? We introduced time, which we didn't have previously. Distances can change as a function of time. They change uniformly, irrespective of where you happen to be. So the metric will look like, on general grounds, the most general metric I can think of, consistent with homogeneity and isotropy, is ds squared is minus c squared dt squared plus some function a of t squared dr squared plus s kappa of r squared d omega 2 squared. So this s kappa represents either positive curvature or negative curvature or flat zero curvature. That's a possibility. This d omega 2 squared ensures that I have isotropy. Things look the same in each direction. This guy is homogeneous, but distances can change as a function of time. Okay. So I can quickly write this as minus c squared dt squared plus a of t squared d c squared 1 minus kappa c squared r squared plus c squared omega 2 squared. So we haven't changed. The other coordinate system I considered. Okay. So this metric is called the Friedman Robertson Walker, or FRW. It's a basic metric in cosmology. So all of cosmology is basically going to be solving Einstein's equations with this metric. Now, A of t has a name. A of t is called a scale factor. Basically tells us how big the universe is as a function of time. And we normalize things so that there's a particular time, t0, which is today, and A of t0 is 1. So the universe has size 1 today, scale factor 1 today. In the past, the universe was smaller, so the universe is expanding, so the scale factor was smaller than 1 in the past. And it's bigger than 1 in the future. Okay, so I want to think a little bit about what time means in this FRW method. Yeah.
Sorry, so just to check, so the isotropy related to that, all the angles being the same and having that spherical symmetry,
Yeah.
and the homogeneity related to what exactly?
Homogeneity relates to the fact that it rotates. So irrespective of where you are in the universe, you'll measure distances the same way. In other words, you can put the coordinate r equals 0 wherever you like. Just like here, isotropy tells you you can put theta equals 0 and phi equals 0 wherever you like. Physics doesn't change. What does change is that because of time, this whole expression can be modified depending on when you are in time. In other words, distances are shorter between points in the smaller universe.
Yes, sir.
Okay, so I want to think about what time means in this FRW universe. and what x, y, and z and r theta phi mean in this universe. So x, y, and z, r theta phi, are given a name. They're called co-moving coordinates. They're co-moving because they're moving in concert with the scale factor a of t. So x, y, z, or r, theta, and phi are co-moving coordinates. And the picture sort of illustrates the concept. So if I have some grid, which is described by coordinates x, y, and z, and I think about this at a time t1, think about what happens at a time t2. Well, the universe might have expanded in the interim. So I've got the same grid, and this is my point, say x, y, z, and this is my point x, y, z. I assign the same coordinates to this point as to that point, despite the expansion. That's what it means to be co-moving. So the scale factor here is a of t1. The scale factor here is a of t2. The scale factor, so time is going up. As time goes up, as we evolve from t1 to t2, the universe is expanding. The universe is bigger. But the coordinates I assign to this point, x, y, and z, stay the same. They're co-moving with the expansion of the universe. So the coordinates stay the same. If the expansion is itself homogeneous, that's the problem. What this means is the expansion of the universe is the same everywhere in the universe. And it's the same in every direction you're looking from anywhere in the universe. So the scale factor is just something which multiplies the distance in the spatial sector. That's why the a of t just multiplies a thing in brackets, which represents a distance in the flat section, in the non-time section. Okay? Yeah.
But then, if you have 2 points, like if the coordinates are the same, and you have 2 points in t1, the length between those will stay the same in t2.
So the length, okay, so if you're measuring 2 points, so let's look at the method again. ds squared is minus c squared dt squared plus a of t squared times the thing in brackets. Okay? What I'm saying is the thing in brackets will stay the same. But a is changed from time t1 to t2. So the distance has changed. A is bigger now. So the distance between 2 points in space-time has, so take this point and this point here. That distance is clearly increased in the picture. What this increase means is that there's an intrinsic distance which has stayed the same. It's just scaled up by the scale factor. And the scale factor is just a multiplier here because the expansion is homogeneous and that's a problem. If the universe is expanding differently at different points in space-time, then I couldn't make this statement. If the universe expands more here than here, the distances change by measuring between a point here and there in a non-homogeneous mathematical way. Yeah?
So in reality, does the universe expand in a homogeneous and isotropic manner?
Yes, it does, in the limit where cosmology applies. So if you're looking at the scale of the solar system, then no, it's not homogeneous and isotropic. We're standing on a planet. Most of the solar system is empty space. This is not an arbitrary, this is not a generic point. This is a special point that we're at. It's not homogeneous where I am. Whereas empty space, it's different. So it depends, the physics depends on where I am. It's not the same everywhere. On large enough scales, the universe is homogeneous in isotropic. It's at those large enough scales that I'm talking about here in describing distances between superclusters of galaxies. Okay, so the expansion is homogeneous and isotropic. The co-moving coordinates stay the same, and the distance in the co-moving coordinates is constant. Okay, so we have just leave this up here. So in this metric, we have a scale factor, A of t, we have a parameter, kappa, and we have a radius of curvature, r. So this is one function and two parameters. So basically all of cosmology is measuring that function and figuring out those two parameters. So kappa basically tells us the curvature, and r tells us okay, so kappa tells us whether things are curved and how. And r tells us how much they're curved. Okay? So it turns out that kappa is very, very close. So in a certain sense, we're working in flat space. The universe is very, very nearly flat in a particular sense. In another sense, we're living in a universe with positive curvature, with positive cosmological constant. So these two senses are slightly distinct, and we'll explore as the course progresses what we mean when we say we're living in flat space, what we mean when we say we're living in positively curved space. So that's sort of the answer to what kappa is. If we're living in flat space, the radius of curvature becomes irrelevant. Kappa equals 0, so who cares? The radius of curvature is infinite if you like, we're living in flat space. If we're living in a positively curved space, there's a positive cosmological constant. So Einstein missed something, and he invented the cosmological constant because he missed something. So if you look at Einstein's equations, the natural solution to the Einstein equations was an expanding or a contracting universe. That's what the equations tell you. Einstein thought the universe was static. The universe wasn't expanding or contracting. At the time, Hubble hadn't made measurements to show that the universe is expanding. So when Einstein was looking at solutions to his equations, he expected a static universe as a solution. So he invented what's called the cosmological constant as a fudge factor in order to cancel the expansion his equations told him was happening. So if he didn't invent this fudge factor, 10 years before Hubble, he would have predicted the expansion of the universe. He missed something. But the thing he missed turns out to be there. So the universe is indeed expanding, but in addition, there is a cosmological constant, which is basically related to the vacuum energy density of the universe. In quantum mechanics, the vacuum is a dynamical thing. The vacuum is creating particles and antiparticles all the time, on short time scales. So the vacuum has an associated energy density. That energy density is the engine which is driving the expansion of the universe today. In fact, the expansion of the universe today is accelerating. Acceleration is given by the cosmological term in the Einstein equations. So even when he misses something and invents the fudge factor, it turns out to be right. He's a very smart guy. Essentially, cosmology is figuring out the behavior of the scale factor and deducing features of the curvature of the universe. Okay, so A of t describes the cosmological evolution of the universe. And I told you that Einstein's equations tell us that matter tells space-time how to curve. So depending upon what the dominant thing is in the universe, whether it's radiation or matter, the scale factor behaves differently. So the solution to the Einstein equation with this geometry depends upon what stuff there is in the universe. So there's some mysterious things here, and mysterious things are really parts of research at the moment. One of the mysterious things is what happens when the t goes to zero limit. So the universe is expanding, at t goes to zero, the scale factor, as you go to t goes to zero, the scale factor is getting smaller and smaller and smaller. The universe is smaller in the past. There was a time t equals zero when the universe began. We call that the Big Bang. We don't really have an understanding of what happened at the Big Bang. We have an understanding of what happened shortly after the Big Bang, where shortly after is about 10 to the minus 33 seconds. Before 10 to the minus 33 seconds, your guess is as good as mine. We have no idea, as a community, what happened in the early universe. So understanding physics in the early universe is really an open problem. So even though these assumptions of homogeneity and isotropy apply, even though the space-time is cosmological, when the t goes to zero limit, we need quantum field theory, say. And gravity combined in some very intricate way. The string theory has some ideas, but again, we don't have the resolution to what happened at the Big Bang. Part of the reason we study black holes is that associated with Big Bang is a singularity. Space-time becomes really, really dense and really, really tiny. So we're hoping by understanding black hole singularities, we can learn something about cosmological singularities as well. But as of right now, there's nothing to report. The other comment I want to make is, the comment that homogeneity and isotropy fail on small scales. So the physics I'm describing is really the physics of the universe at distances larger than 100 megaparsecs. For distances smaller than this, there's no invariance in space. Different directions and different places look different. Some places are more dense than other places. Some places are less dense. For example, if you're in a galaxy, you're in a dense environment compared to the space between the galaxies. And you're sensitive to these effects at scales smaller than 100 megaparsecs. So this whole notion of scouting metric distances in space-time is really only applicable to large-scale physics. So any questions?
So
Yeah.
I was thinking about the general covariance.
Yes.
Doesn't it just directly follow from Einstein's postulates from special relativity?
No, it's more than special relativity. General covariance is a statement that there's a symmetry that you associate to space-time. The symmetry is that there's this, so I'm trying to answer the question before. Special relativity basically tells you that any inertial reference frame, laws of physics are the same, and in particular, the speed of light is the same, any inertial observer, any observer. So this is a consequence of basically electrodynamics. So Einstein's original paper on special relativity is called On Electrodynamics of Moving Bodies. So you look at electromagnetism for moving bodies, electromagnetism involves light, you're seeing how this behaves. But he was talking essentially about inertial reference frames. Here, for example, in my falling elevator, or my elevator or rocket ship or whatever, I'm not talking about inertial frames, there's acceleration at the end. So that's a key difference between special relativity and general relativity. General relativity is basically the equivalence principle, firstly, that you can make an identification between inertial and gravitational masses. It's also a statement that there's a diffeomorphism invariance. This diffeomorphism invariance is also called general covariance. So before this theory of general relativity, the coordinates you assign to events matter. Here, general covariance tells you that the distance between events matters in space-time. But the actual coordinates you assign to events is just a choice you're making. It's completely arbitrary. That's basically the heart of this idea, that events in space-time are physical things. So if something breaks, two different observers agree that they break. Two observers may assign different coordinates to when the thing breaks, but they agree that it breaks. The breaking of the thing is an event in space-time, which is coordinate independent. The relative distances between, say, launching a rocket and the rocket hitting something, that distance is something observers will agree upon, even if they disagree upon when the hit happens. So the distances between space-time events is a physical thing. And the physics of these physical things is what general relativity is a theory of. Okay? And this theory applies in an arbitrarily curved space-time. So the assumptions that underlie general relativity are that space-time is smooth. So it's smooth in the sense that, okay, so one function on space-time is the metric. The metric takes two vectors, so x and y are coordinates in space-time, and it gives us a distance between x and y. Okay? So x is equal to, if you like, t1, r1, theta 1, phi 1, then y is equal to t2, r2, theta 2, phi 2. I take these two vectors to describe events in space-time, and I measure the distance between them. I measure the distance with g. G is basically the metric line element. As a matrix. So I have two different vectors. I have a row vector, a matrix, and a column vector. When I multiply the matrix with the column vector, I get another column vector. Multiply the row vector with this new column vector, I get a number. That number is the distance between 2 points in space-time. I construct this matrix out of my ds squared. So if you like, the ds squared is minus c squared dt squared plus a of t squared dr squared plus s kappa of r squared d omega 2 squared. I can write my matrix as minus c a of t, s kappa of r, a of t, I guess u squared, s kappa of r squared, sine squared theta. Okay, so if I take my row vector, dt, dr, d theta, d phi, and I take a column vector, dt, dr, d theta, d phi, and I multiply things out, I'll find it at minus c squared dt squared plus a of t squared dr squared plus s kappa of r squared d omega 2 squared. So this is ds squared. So converted this line element I wrote previously into this matrix here. Okay? This matrix takes two vectors and gives me a number. So that's what this guy G here is. Okay? So in writing down the Einstein equations, I'm assuming I can differentiate this function. And I can differentiate this function in a way that there aren't any singular points. It doesn't blow up anywhere when I differentiate it. So that's what I mean when I say space-time is smooth. The distances I measure between points is given to me by the smooth function. That assumption starts to break down when the universe is very, very tiny. There's a singularity. So space-time ceases to be smooth in the limit where the scale factor a of t goes to 0. That singularity we call the Big Bang. So the assumption that Einstein made that space-time is smooth breaks down in a certain setting. And in that setting, the Einstein equations aren't valid then, because the assumptions that went into the Einstein equations no longer apply. Okay. So I want to emphasize a couple of things here. One thing is that Einstein never said Newton was wrong. So Einstein basically just said Newton was applicable in a certain regime of validity. And that regime of validity is not every regime of validity. So the limit of weak curvature Newton's laws are valid. Einstein's corrections of Newton's laws that describe, for example, the orbit of the Earth around the Sun are very, very tiny. So for most practical purposes, it doesn't matter. However, if you're thinking about something like GPS, which is in your phone, then it does matter for certain purposes. Measuring distances by triangulation that involves general relativity. So, you know, if you want to adapt the equations to the orbit of planets, Newton's laws are good enough. If you want to make more sensitive measurements, then Einstein's equations give you better refinements. So, you know, a lot of the work Einstein did was just out of curiosity. How does gravity look like acceleration? Then you come up with a thought experiment to examine how acceleration is related to gravitational forces. So a lot of what the theory was developed to do was just to satisfy the intrinsic human curiosity to figure out how things work. The fact that it's useful is a very interesting and very lucky consequence of the theory, but it wasn't the purpose of the theory. So, you know, this is something which, when you guys are people determining whether scientists get funding or not, keep that in mind. The fact that things become useful is something you learn decades after the thing is developed. It's not that things are immediately useful. So, if you want to fund research that answers interesting questions, because it turns out that answers to interesting questions do end up being useful. It's just that it's hard to figure out how and when this happens. So we've developed this theory, which lets us measure distances in homogeneous mesotropic curved spaces. So now we're going to apply this formulation for how to measure distances to studying how the universe behaves as a function of time. So that's where we're headed. Tomorrow, I guess we're meeting again, right? So tomorrow we'll discuss how to measure distances in FRW universes. Something called proper distance. I'll post my lecture notes, and I'll also post a tutorial for next week on the course page. And if I get around to editing the videos, I'll post them too somewhere. Probably on YouTube, since Wits network as well. Okay, any questions? Yeah.
Professor, can you please return to that concept of the distance lifetime between 2 points being 0?
Okay.
I'm curious to ask, does that mean you're considering that light ray as a series of photons as opposed to just one?
So, it doesn't actually matter. I don't know any answer like that. Let's just say that they're. Okay, so if you look at the way ds squared is written, there's a minus sign there. Because you're adding something which is negative, something which is positive. The result can be one of three things. The answer can be negative, the answer can be 0, or the answer can be positive. Okay? So, by construction, if the answer is 0, then this is what's called a null geodesic, right? So, null geodesics, by construction, are what light travels along. If you think about the distance being positive, we say the separation is space-like. We say space-like because the terms which involve spatial coordinates come with a plus sign. And those coordinates dominate whatever is negative. So the resistance is space-like in a sense. If it's negative, we say time. The time coordinate is what dominates the spatial coordinates. Time coordinates comes with a minus sign, and the result overall is negative. Okay? Yeah.
So in which case would it be negative? Would the distance be time?
Okay, so if we consider 2 points in space-time, so let me not answer this one again. Let's think about us sitting here. Okay, we have a flashlight with us. We shine the light. The light follows null geodesics, so it traces a curve, say. So there's a cone, which is defined by the rays of light. So everything in this cone are points we can communicate to in space-time. Okay? So we can, because this is light traveling, we can delay our signal, and we can still reach this point in space-time with a ray of light later. Okay? Similarly, we've got a past cone. These are points in space-time from which light can reach us within the history of the universe. Okay? So you look backward in time, you can only see points in your light cone. Because we measure things in the universe with telescopes. Telescopes collect light. So light has to connect that point in the past to us today. Similarly, we're shining light out, and we reach other points in space-time. Points that are along this light cone, this is where light is traveling. So 2 points here and to us are null separated. Okay? Now, space light and time light refer to whether you're inside the light cone or outside the light cone. So if you're communicating to a point here, that's time light separated. To go from here to here is light following time. If you're talking to a point here, well, in order to reach that point, you need to travel faster than the speed of light. Send a signal faster than the speed of light. That point is space light separated.
And we can never reach it.
We can never communicate to such a point. Okay, so let's in fact show this is the case. Let's assign coordinates 0, 0, 0, 0 to ourselves here. Okay? And let's assign coordinates here to be t1, t, x, y, and z. For convenience, let me set y and z equals 0 by choice of coordinates. Okay?